Today we're going to do something a little bit more fun. What I'd like to do is show you some computer code that I use to implement what you see here. So what we're going to do is we're going to implement the Helix wave. Okay, we're going to implement this in on the computer. And I know historically people have asked me if I could share my code with them. And up to now I've said no, only because I've been implementing my code in a platform that I use for work, and I am not allowed to give away the code from work because there's some proprietary stuff in there. And so what I did was I implemented the Helix wave in a tool called P5JS. So this is the P5JS editor, and what I'm going to show you is how I implemented this here on the right. Okay, so basically this is a, it looks like a sine wave, but when you rotate it, you can see that it is in fact a spring. It is a helix wave. And when you look at it from one side, exactly one side, let's restart this so I get it orthogonal, then what you see is it just looks like a sine wave. So when you look at a helix wave from the side, it looks like a sine wave. Okay, so this is what we're going to play around with today. So basically what the software is doing is it is orbiting circles around a plane, an XY plane. Okay, so what we're doing is we're rotating a circle around a plane, and we're propagating the plane from Z left to Z right. So this is the Z direction in my coordinate system, and we're going to talk about coordinate systems in a second. Okay, so this is the time direction. So the this plane is propagating from left to right, okay, and it is generating the helix wave. So here is a picture of the two-dimensional plane that you see, that we see here. Okay, I'm just showing it face on, and I'm going to show you how I use the 2x2 matrix version of Euler's formula to do this rotation. Okay, so in this setup here, we've got the real axis is horizontal, and the imaginary axis is vertical, and the positive real points to the right, and the positive imaginary points up. And so in order to do these animations, I think it's important to have a standard. Okay, and so I'm going to tell you, before we look at the code, I'm going to tell you the standard that I'm using in the code. Okay, and so it's very important to have a coordinate system when you're doing computer graphics, and so we're going to talk about the right-handed coordinate system that I'm using to generate these animations. Okay, so here is a picture of the right-handed coordinate system. Okay, so X is on the horizontal and Y is on the vertical. So X is real and Y is imaginary. And I want to remind you that in the 2x2 matrix version of Euler's formula, the real is on the forward diagonal and has the same sense, and the imaginary component is on the backward diagonal and has the opposite sense. So in a right-hand coordinate system in 3D space, in 3D Cartesian coordinate system, what you do is you take your right hand, and you point your fingers in the direction of, so you put your hand in this orientation here, and if you stretch out your fingers are going to point in the direction of positive X. And then if you curl your fingers up, your fingers are now going to be pointing in the direction of positive Y. And when your hand is in this orientation, your thumb is going to be pointing towards positive Z. Okay, so the rotations are going to be happening in the XY plane, and the propagation, okay, the propagation is going to be happening in the Z direction. Okay, so we could alternatively, so let's just talk about coordinate systems for a second. Typically, 3D graphic applications use two types of coordinate systems, left-handed and right-handed. In both coordinate systems, the positive x points to the right and the positive y points up. You can remember which direction the z positive points by pointing the fingers of either your left hand or your right hand in the positive x direction, as I showed you, and curling them into the positive y direction, as I showed you. The direction of your thumb points either points towards you in the right-hand coordinate system or away from you in the left-handed coordinate system. Okay, so you can see that right here. So when you're doing computer graphics, it's very important that you get your coordinate systems right. Okay, so I work in the field of medical imaging, and I deal with 3D ultrasound images, 3D MRI images, and 3D CT images. And if I want to register an ultrasound image to an MRI image, for example, they both have to be right-hand coordinate systems. Okay, if one, I remember back in the day I had an image, it was a CT image, and I couldn't register them, I couldn't figure out why, and that's because the CT had a left-handed coordinate system. And so then I had to convert it to a right-handed coordinate system in order to register to the 3D ultrasound image. Okay, so it's very important to, and most people use right-handed coordinate systems now in computer science and medical imaging, and so this is what we are going to use here. So what I'm showing you here, what I've done here is I've placed a circle, I've placed a dot on the x-axis, on the x coordinate, and I placed it at x equals 1, so this is the unit circle, x equals 1, and y equals 0. And so the real component is the x, and the imaginary component is y, and so real is equal to 1, oh, let's go back to this one, real is equal to 1, and imaginary is equal to 0. And so what we're going to do is we want to rotate this dot around the circle, and we are going to rotate counterclockwise about the z-axis. Okay, so we're going to rotate counterclockwise to match this diagram here, because in this diagram here, the helix wave is spinning counterclockwise as it propagates from left to right. So let's say we want to rotate the point from here to here. Okay, so this is not quite 45 degrees. This is about maybe 30 degrees. So what we're going to use Euler's formula, the 2x2 matrix version of Euler's formula, which is a transformation matrix, okay? And we're going to take this point 1, 0, 1, x equals 1, y equals 0, real equals 1, imaginary equals 0, and we're going to multiply it by this matrix, and we're going to get an output matrix, okay? And so the way you do that is you go x times the cos of theta plus y times minus sine of theta, so x times cos of theta minus y times sine of theta, and then that becomes the new x value, and you take x times sine of theta plus y times cos of theta, okay, x times sine of theta plus y times cos of theta, and that becomes the new y. So this is the formula we will be using to rotate this point counterclockwise by a predefined angle that we specify. So in the software I'm going to show you, I also need to be able to rotate these points clockwise about the z-axis. Okay, so I've got two waves in my software. One is going to be propagating in one direction, and one is going to be propagating in the other direction. And in order to draw both the waves, one is going to have to sort of orbit the z-axis counterclockwise, and the other one's going to have to orbit the axis clockwise. So in order to do the clockwise rotation, what you do is you take the complex conjugate, you multiply the point by the complex conjugate of Euler's formula of this matrix. And so the complex conjugate is you put a negative sign here and a positive sign here. Okay, and so in essence what that's doing is it's putting a positive sign here and a negative sign here. Okay, so this is all taken care of in the code. So basically, if you want to go counterclockwise about the z-axis, and of course the positive z is pointing to in the direction of your thumb here, then you would use this version of Euler's formula. And if you want your point to orbit clockwise about the z-axis in this coordinate system, then you would use the complex conjugate. You would put the complex conjugate into the transformation function, okay, where this would be positive and negative would be right here. So what we're going to be doing is we're going to be implementing two helix waves, okay, two wave functions. One is going to be propagating from left to right on my screen, and one is going to be propagating from right to left. So here you can see there's the yellow-red wave is propagating from left to right, and the blue wave is propagating from right to left. So here we're using a toolkit called P5JS. Okay, a P5JS editor is used. Basically, you just plug the code into the P5JS editor and you run it. So if I stop this, I'm going to run it, and you will see here is my wave patterns on the screen here. And so when you run the P5JS editor without any code, you get sort of a bare bones application right here. And so you can see that there is a setup function and a draw function, and this is pretty much all there is to P5JS. Okay, if you run this, all it's going to do is draw a gray square on the screen that is 400 pixels by 400 pixels. Now if I change this to say 500, and I change the color to 0, which is black, then you're going to get the background is going to be painted 500 by 500 pixels, and the background is going to be 0. So as you can see, the code that I wrote is a little bit longer than the default code. We're just going to go through this quickly. I'm just going to show you sort of the outline of the code, and then we'll get into the details. So the first part of the code is the setting up the variables and initialization. Okay, so that is sort of at the top of my code here. And then we have the setup function. Okay, we have a setup function just like in this one, only it's setting up for drawing these two waves. Okay, I've got an initialize wave 1 and initialize wave 2. We'll get into the details in a minute. And then we have the draw function. And so what happens is you've got a frame rate timer, and on a timer, it calls this a draw function over and over and over again. So it is calling the draw function in on a timer, and then for each iteration it draws the wave at whatever location it happens to be. Okay, and then so then I have excuse me, I just woke up and my throat's a little gruggly. I have an initialize wave 1 function. So in the setup function I have initialize wave 1 and initialize wave 2. Okay, so I've got initialize wave 1, which is the yellow-red one, and then I have initialize wave 2, which is the blue one. And then I have the draw wave 1 function, which draws a wave 1, and the draw wave 2 function, which draws the blue wave going from right to left. Okay, so you've got one wave moving left to right, you've got one wave moving right to left. But these are not, although these look like sine waves when looking at it from this view, these are in fact helix waves. Okay, So there's two helix waves that are moving in opposite directions, and sometimes they coincide and sometimes they don't. And so I've got a few functions in here to show you the three orthogonal views of the helix wave, and so you can see you can maneuver using the mouse, you can maneuver these around, and you can have a look at these waves as they are, one is propagating, say, towards me, and the other one is propagating away from me. And that is what, when you look at a helix wave from the side, okay, it looks like a sine wave or it looks like a cosine wave. If you look at it from the top, if the side looked like a sine wave, the top is going to look like a cosine wave. But these are in fact helix waves. Okay, this kind of looks like a double helix actually when you look at it from this view, which is kind of cool. So next what we're going to do is we're going to enable this function, the draw interference wave. Okay, we're going to enable it. Right now it's disabled. And just so you know, when you're writing P5.js code, this is very similar to C++, the double / enables or disables a function. So when I put the two / in front of a function, it actually disables that function. It doesn't run that function. So we're actually now going to run that function. Okay, so here is the looking down the barrel of the gun of the two helix waves and the interference pattern. Here's the side view of the two waves and the interference pattern. So as you can see, the interference pattern, the purple wave here is the interference pattern between the yellow-orange wave and the blue wave. Okay, that's pretty straightforward. Because we've got the same, each wave has the same wavelength. There's two waves in the screen at any one time for both of the waves, and that is what we set up here. So the number of waves on my screen at any one time for the red wave is 2, and for the blue wave is 2, and this is the interference pattern that you get. Okay, so now I'm going to actually just set the number of waves to 1, so you only see one wave on the screen at any one time. So here you can see you've got these circles. So what I'm doing for each wave is at the ends here, I'm just drawing a little circle at the end of each one, so that when I look at the barrel of the gun, I can see which direction. When I look down the z-axis, the red wave looks like it's moving counterclockwise, and the blue, the circles on the wave look like they're moving clockwise. So just so you know, I think this is important, these waves are actually made up of tiny circles. Okay, so right now I'm setting the number of spheres. They're actually spheres, not circles, they're spheres. If I take this down to say 100 instead of 1000, then you're going to see that the waves are made up of tiny circles. And of course the animation can go much faster because I'm not drawing as many spheres. So the more spheres I draw, the slower the animation is, because it just takes longer to draw that many spheres. Okay, so this is running at 60 Hertz, and so there is going to be a limitation as to the speed of these waves depending on how many circles I draw. So I'm going to go back to drawing 1000 circles along the wave. So each wave consists of 1000 circles, and when you put a lot of circles in, it just looks like a continuous line, which is nice. And so then I redraw excuse me, a circle at the end of the blue, or at the end of the blue. That's actually the beginning of the blue and the beginning of the red wave in the helix wave. Okay, so let's just have a look at this from the barrel of the gun. So here you can see that the circles on the blue wave are moving at the same rate as the circles on the red wave. And so if I make, let's say I make the first one 1 and the second one 10, you can play around with this one and give you the code. You will see that you'll see this pretty pattern, which looks kind of like a ferrocell image, which is kind of cool. You will see that the blue circles on the wave spin around the circle Okay, they spin around the circle 10 times for every 1 time that the red spins around the circle. And when you look at it down the barrel of a gun, you see this pattern, but when you look at it from the side, you see the wave. Okay, you can see here the first wave is only 1 wave on the screen, and the second wave, the blue wave, has 10 waves. Okay, and then you can see that the purple wave is kind of riding the red wave. And so what I'm going to do is I'm going to actually disable the blue wave here. I'm going to just turn this to false. I don't want to disable this because there's some computations that I'm doing in DrawWave 2 that the interference wave needs, and so I just set this to false, and I just don't draw. Although I do the calculations, I don't draw the blue wave. Okay, so now the blue wave is gone, and you can see that the interference pattern, which is the purple one, it has 10 waves that are riding 1 wave. Okay, so you can see the combination of the 10 waves and the 1 wave in the interference pattern. So the interference pattern looks like the 1 wave, but it also has 10 waves in it. Okay, so this is kind of cool. You can play around with this, and you can, you know, just try different patterns. You can plug different numbers into these number of waves and see the different patterns. And of course, when you look at this wave down the barrel of the gun or down along the Z axis, you will see this pattern. And of course, that pattern is kind of an optical illusion, because in reality, you've got this helix wave, and now the interference pattern is sort of a helix wave on a helix wave. So this helix wave is riding the other helix wave, which is again kind of cool. Okay, so you can see that. You can move this around, and you can see, now I'm going to flip through the orthogonal views. Now in my code, I set up the letter C, as in E equals MC squared. The C, I have a little bit of a lisp, so the C on the keyboard allows you to flip change the 3 orthogonal views. So that's the looking down the barrel of a gun, that's from the side, and that's from the top. Okay, and the side and the top are going to look 90 degrees out of phase with each other, as you would expect by looking at this here. So you can see when you look at the side of a helix wave, it's going to look like a sine wave, and if you look from the top, it's going to look like a cosine wave. Okay, and so basically what my code is doing is it's taking a point on a circle. It's starting at an arbitrary starting point, and it's orbiting around this circle. I start with the unit circle, and I change the amplitude depending on what I choose the amplitude to be, and I'll show you the code for that. Okay, and I am propagating from one end of the z-axis to the other end of the z-axis, and so each point along this path, each position, each z position, I will be drawing a sphere, and that sphere is going to be somewhere on this unit circle. Okay, it's going to be some phase angle, it's going to be some angle, some phase angle, relative to the starting location, which is x equals 1 and y equals 0. Okay, so this is going to be my starting position for all of my helix waves. So in terms of implementation, what I have here are 2 arrays. I create 2 arrays. One for the wave, the red wave that's propagating from left to right, and one from the blue wave that's propagating from right to left. So let's re-enable the blue wave for a second. I'm going to disable the interference wave just for a second, and then we'll have a look. Okay, so I have, going from left to right, I have 1 wave, and going from right to left, I have 10 waves. And we could easily change that back to 1, so which is a little easier to see. So we've got one wave moving from left to right, and we have one wave moving from right to left. Okay, and so that's these parameters here. I also have, you can set the amplitudes for each wave. Here I set them both to 100, but let's say I set the second amplitude to 50. Okay, it's going to be half the amplitude, so you can see from this view, it is the blue wave is much smaller than the red wave, and when you look at it from the side, you can see that the blue wave is shorter than the red wave. And then we can go and re-enable the interference pattern, and we can see what that looks like. Okay, so let's look at that from the side. Now that looks a little strange, right? It doesn't, this looks like a standing wave, but it also looks like the interference pattern kind of looks like it's traveling as well. It kind of looks like when you take a piece of paper and you create a wave with a piece of paper, it kind of looks like that. And so you can play around with those parameters. Let's just try maybe a couple more for fun. If I just set this to 1, let's see what happens. Okay, when I set this to 1, what happens is the interference pattern propagates is almost exactly the same as the wave that is traveling to the right. Okay, so when the amplitude also affects the interference pattern, I guess is what I'm trying to say. So now if I make this a little bit bigger, maybe I'll make that second wave 10. So there's going to be 10 waves. Okay, and you can see that the amplitude is 10. Sorry about that. The amplitude is 10 for the blue wave, and the amplitude is 100 for the red wave. So the blue wave, the purple wave, the interference pattern is kind of following this one, and it's kind of following this one. And so as we make this bigger, let's make this maybe 77. Okay, and then you'll see that it is very close to being the standing wave again, but you still get that kind of feeling that it is a standing wave because the amplitude, the largest amplitude, always ends up at the same place. See how where my cursor is right here, and this wave, even though it kind of looks like it's propagating, when the two waves have very similar amplitude, it's looking like this amplitude is not, the peak is not propagating, it is ending up in the same place every time at each cycle. And so it's it's a hybrid standing wave, propagating wave, I guess you could say, this interference pattern. So this parameter here, the master phase increment, is used to speed up and or slow down the propagation of the circles around the z-axis to make the helix wave. And so if I set this to 0.7 instead of 0.07, you're going to see the circles moving really quickly around in circles, and you're going to see a very fast propagation of the two waves. Okay, so we can slow them down. Let's say I could go to 0.01. Okay, and then you're going to see the circles are moving very slowly around the helix wave. So all these circles, okay, all of this orbit around the z-axis is going to be faster or slower depending on what I set this phase increment to. So what this does is it every time I go through that timer loop, it is going to move the circle just one more increment, one more 0.01 degrees, I guess that would be. And so you see them moving really slowly here. Okay, so the waves are now propagating extremely slowly. So I had it set to 0.07, and I like that speed. That's a speed that's not too freaky. It's a very natural speed, and so that's why I set this at 0.07. So these are all the main parameters that you can manipulate right off the top when you download the program. I recommend that you start with playing around with these values here. You can make the window bigger if you want a bigger window. Okay, if you want this to be a little bit bigger, you can do that. if you want to change the number of waves associated with wave 1 or wave 2, the red wave and the blue wave, if you want to have, I don't know, 1 in 10, okay, which actually this makes this very beautiful pattern when you're looking down the barrel of the gun. I like when you set a 1 to 1 and you set another one to, let's maybe go 22. Okay, you get, actually that looks very electric. That looks really cool. So what you get is this sort of hypertrochoid pattern that Ken Wheeler talks about, and also that you often see this in the ferrocell images. Kind of like what you see here in my paper, the Demystifying the Ferrocell paper. Let's go to the beginning here. In Demystifying the Ferrocell, which is on ResearchGate, okay, I generated these images. Which look an awful lot like the image that I'm generating here, which is the looking down the barrel of the gun of two interfering waves. It's an interference pattern. One wave has 22 waves, the other wave has just 1, but you can see that in fact the 2 waves are, these are helix waves, okay, and this is the propagation direction. In fact, there are 2 propagation directions, one for the red wave and one for the blue wave. They are moving in opposite directions, which is creating the interference pattern that we see as the purple wave, okay, which looks like that. So the purple wave is the interference pattern of the red wave and the blue wave. Now the blue wave is a little bit smaller because it was set to 77. So the red wave is 100 pixels and the second wave, the blue wave, is 77 pixels, and that is the amplitude. So that is the amplitude that we multiply the unit circle. So whatever we have as our starting point for the x in, or the y in the unit circle, then this we multiply by this to get the amplitude. So what I'm going to do is I'm going to end this video because it's getting a bit long, and I want to get this video published, and I want to get this code to you. So what I'm going to do is I'm going to put this code into the description section of the video, and I will give you a link to the P5.js editor so you can play around with the code and you can try different parameters and make some pretty pictures. And if you get some really neat pictures or some really interesting effects, I would like to see them. So please feel free to share anything that you discover with this code. If you make any changes or make any other discoveries or find any bugs, then please let me know. If I need to, I will maybe make another video and get into more details about how it works. It's actually pretty straightforward, and so if you have any questions about the code, feel free to ask me. And I just want to get this out to you. I've been holding off finishing this video, and I just want to finish it and get it out to you so you can have fun playing with this code. Okay, so I will leave it at that, and we will talk soon.